welcome back to Introduction to Computer Networks. This is Polly again, your instructor. Yeah, so let's check out the announcements again. Just like, oh, hi Sophia. Hi. Yeah, so as usual, we have the links to the lecture and the Google Meet session. Hi Jeremy, you guys are early. Oh, there you are, yeah. Yeah, so you might notice that Polly tries to be punctual starting the video sessions. Okay, and I figured out how long these background musics are, and so I'm looping it at the right time so that it will end right at the time we're supposed to start the lecture. Okay. Hi, Sylvain, Ting Yi, Nicholas, Yan Qi, O. Zhen Yu, Tao, and Kaze, and Miguel. Yeah. All right, and just one more point today. So I don't know how fast the lecture is going to go today. It might be a little bit faster than usual. Hi, Zach. Hi. So in case we are faster than what I had expected, we might need to adjust the videos you guys will need to watch next week and the scope of the quizzes. Okay, you're supposed to work on next week. Otherwise, I do want to draw your attention to exam 2, which is coming up in 2 weeks. So if you go to the exam 2 channel, you will see the scope of the exam. Okay, as I mentioned that it's non-overlapping, but that's not 100% true. In terms of the theory part, okay, of the lectures, it's non-overlapping. But in terms of the PA, there'll be a slight overlap, that is PA number 3. Because to test you guys the system calls in PA number 4, it's better that you have PA number 3's system calls to work with that. So the scope for exam 2, the PA part is slightly overlapping, okay, not exactly non-overlapping, okay, just that you guys know. All right, now the topics today. Yeah, so yesterday we had a very exciting quiz that asked you guys to guess the prices of some items given some hints, right, from Polly. Similarly, TCP controls the sending rate given the hints coming from the network. And so in the steady state, you learned yesterday that TCP controls the sending rate in this AIMD fashion. Okay, additive increase, multiplicative decrease. The first video today is to talk about, hey, steady state. Then the opposite of that is the non-steady state. And that is what we refer to as the initialization state, because when the TCP connection is starting, it always starts with the low window size to begin with. And you probably want to quickly ramp up to the steady state sending rate. That'll be better, right? Otherwise, then you are underutilizing the network channel. And that phase, initialization phase or starting state versus steady state, runs in this slow start mechanism. Okay, so this video, about 3.5 minutes, talks about slow start. Something that's a little bit unusual in TCP's process of discovering the proper sending rate is this. There's an initialization phase. And the mechanism is called a slow start. Okay. What it does there is, when TCP is just starting, a connection is just starting, the initial window size is set to 1 MSS. And the increasing pace is no longer AIMD, it's actually what? Doubling the window size per round trip time. AIMD is what? Increasing the window size by 1 MSS per round trip time. Wow, so that's actually quite aggressive, isn't it? You are correct, because the window size in slow start in the initialization phase is going to increase exponentially, because every round trip time you double the size. Every round trip time you double the size, as opposed to in AIMD, every round trip time you increase by 1 segment size. Every round trip time you increase 1 segment size. Right, so yeah, the initial rate, very, very small. 1. So slow start is actually referring to, yeah, the initial window size being, yeah, the lowest possible.
but the increasing rate is actually exponentially fast. Okay, so this is actually the part of designing TCP's condition control that can confuse you a little bit. It's slow start, but it's actually increasing really, really fast, right? So the intuition says this is fast start, in fact. Yes, you are correct, but the slow here actually meant the window size, the initial value is a very low value. The last point I want to make is this. Doubling window size per round trip time in the implementation is actually done this way. Window size is incremented by 1 after receiving an act. So look at the illustration I have on the right. A is the sender, B is the receiver. A originally in slow start having a CWND of 1 MSS. That data packet will go, receiver here will send an ACK back. Host A here being the sender, receiving an ACK will do what? CWND plus plus, and the increment is 1 MSS. As a result, it was originally 1, now 2. Therefore, sender here can send 2 segments in MSS. So these will go and generate 2x coming back. Sender here receiving 2x will be calling this line twice, therefore 2 will become 4. Similarly, 4x comes back here, and this will be called 4 times, therefore the window size becomes 8. And the next round, 16. You see an exponential increase here, right, by a factor of 2, isn't it? So overall, TCP's process of discovering the proper sending rate is more like this. This is a TCP connection, and this is the beginning of it, and this is the end of it. So there's this initialization phase where we run the slow start mechanism, okay, and the behavior of the window size is AIMD. And then in the steady phase, we run this congestion avoidance mechanism. The behavior of the window size is AIMD.
Right. Yeah, so hey, Polly is a little bit embarrassed hearing herself saying AIMD when I'm actually pointing to EIMD. Yeah, so excuse Polly, sometimes you just, talk not in a very precise way. Well, hey, that was a slow start. Okay, it's working in a EIMD way, but the steady state AIMD. All right. And the next video talks about how TCP detect losses, and there are 2 kinds of losses TCP detects in order for the congestion control mechanism to react accordingly. Okay, and now if you recall, the RDT side of TCP, reliable data transfer side of TCP, how do we detect packet loss? Yeah, we set a timer, right? If the timer expires, there we detect a packet loss. And so that was building in TCP's RDT. But you heard also that towards the end, there's an improvement called fast retransmission, right? When TCP detects a packet loss by timeout, what do? We retransmit the packet. There's a fast retransmission mechanism that triggers retransmission, so in a way detects loss and therefore retransmit in a very different way, which is to see if there are 3 duplicate ACKs. Yeah, so this video, okay, try to be explicit about 2 different kinds of packet loss being detected.
And you heard probably Polly saying, yeah, TCP increases the window size when there are no losses and decrease when there's a loss. But if you think a little bit carefully, in TCP, the sender detects a packet loss 2 ways. One is, yeah, there's a timer set when the packet is sent. When the timer expires, the sender there discovers the packet is lost and then retransmit. But in TCP, there's something also called fast retransmission. We are retransmitting packet faster right after receiving triple duplicate ACKs. So there are 2 ways in TCP sender to detect a packet loss. In fact, in TCP's congestion control, we are also adjusting the window size differently depending on which type of loss is being detected. First is, a loss being detected by sensing the timer timeout. We then set the window size all the way down to 1 segment, okay? and then grow exponentially just like in slow start state. After a certain threshold, then grow linearly just like in the congestion avoidance state. On the other hand, when the loss is detected by seeing 3 duplicate acts, then the congestion window is actually cut to only half the current window size, not all the way down to 1. And then grows simply linearly. So this is very much like what? AIMD. Yeah, you're actually right. When the loss is detected this way, the TCP sender is actually dropping the sending rate to half and then continue on with the AIMD, therefore, into the CA state, the congestion avoidance state. So the TCP connection here is still in the steady state. But if the loss is detected this way, it appears that the TCP thinks this is actually a more serious scenario, therefore the window size needs to go all the way down and then being reinitialized, okay, until the window size grow to a certain degree. Then we do the AIMD like in the steady state. Okay. Now, based on your intuition, which loss of these two you think is more serious? Yeah, I know, it's quite obvious, right? Because in this case here below, at least you get to receive 3 duplicate acts. That indicates the network is still capable of sending 3 packets through. Therefore, you get 3 acts back. But this scenario here, it's top. You don't get any data through, you don't get any data back, or you get only 2 duplicate acts back. So, yeah, more serious. Therefore, Windows drop down even more aggressively, all the way down to 1, and that's restart, reinitialize again. Now, the only thing that you thought, interesting is this. So we have not yet defined what is this threshold yet, because it seems that this threshold is there to determine how a TCP connection there start from the initial state, entering the steady state. So that is also the point to decide. When do we change the mechanism from slow start to congestion avoidance? First point to add to the slide is this. The threshold in TCP's implementation is called SS thresh. You guess, S and S here actually meant S and S here in slow start. Second point, the whole mechanism differentiating how we adjust the window size depending on the type of loss being detected is implemented in TCP Reno. Yeah, I know. TCP designers is a bit weird. They like to call different versions of TCP with names instead of using a number. So Reno there is essentially the version 4, TCP version 4. There's another version of TCP, TCP Tahoe. So this is actually the first generation. So what's being designed there is this. The loss, no matter whether it's detected by timeout or 3 duplicate acts, the window size is adjusted the same way, always down to 1. That means Tahoe there is very, very conservative. Whenever there is a loss detected, the sender always go down to the lowest rate possible. And that might be a bit too slow based on experience, therefore in the second generation. The designers begin to say, hey, maybe in this easier case, at least we see 3 data go and then 3 duplicate acts back. It's not so bad. Let's only cut the window size to half and then remain in the congestion avoidance phase.
Okay, double investment today. Yeah, so that was version 2, but Polly was saying version 4. No, TCP doesn't have a version 4. Okay, so Reno is version 2 and Tahoe is version 1. And you see there that, hey, in AIMD that talks about the mechanism of increasing, right? But decreasing is multiplicative. Okay, in EIMD initial state, we talk about how the window size is incremented by 1 per act, right? And the decreasing is also multiplicative. Okay, but in the previous video, you see that. Yeah, that's generally true when it's the kind of loss that you detect 3 duplicate acts, then you drop to half. In case it's really serious, it's the timeout type of loss, then you always go down to 1. And then try to slow start again. All right. So in dealing with the losses, there's a subtle difference. It's not strictly always multiplicative decrease. And this last video about TCP's condition control talks about the transition from the initial state to the steady state, which you heard a little bit about. It depends on the SS thresh. Okay. Yeah, Miguel, I'll come back to your question after we play this video.
So what I'm illustrating here is TCP Tahoe's window size changing over time. At the beginning, window size set to 1 segment. And then slow start, right? This is the initial phase. And therefore you see exponentially fast growth, the concave curve. And this is going to go until we hit the slow start threshold. That's when we exit slow start and enter congestion avoidance, where we do AIMD, so additive increase. At this point, we detect a packet loss due to 3 duplicate acts. But in Tahoe, we'll just drop the window size back down to 1 again. And then slow start again, a concave curve, until we hit the threshold again, and then AIMD again in the congestion avoidance state. Now, what's in Reno is, however, when we detect 3 duplicate acts, a packet loss, what we do is more simple, where we just reset the window size to half of the original window size, which is 12. So we set it to 6, and then continue to grow the window size AIMD, such as in the congestion avoidance state. Okay. Now, by looking at this plot, you also see, hey, we are switching from the slow start to the congestion avoidance state using the threshold. At the beginning, the SS thresh is initialized to a fixed value. But afterwards, you see the SS thresh is also changing. And when we detect a loss, when we need to reset the congestion window size down to some lower value, when that happens, when the packet loss is detected, the threshold here is also reset. And the value is set to exactly half of the window size before the packet loss is detected. So SS thresh is set to half of the window size just before the loss event. Okay. So in the TCP Reno's case, it's convenient. We set the threshold to the half of the window size, and we also set the window size to half of the earlier window size and continue to grow like this. So it's also saying passing the threshold and then this connection in the congestion avoidance state. If we go back to the original question asking, when do we switch from the slow start state to the congestion avoidance state, or from exponential increase back to linear increase? And so it's very clear. Once the congestion window hits the SS thresh, the slow start threshold. Because if you look at this, slow start, passing the thresh, growing linearly. Slow start, passing the threshold, growing linearly. And in this case, we see 3 duplicate acts, therefore we drop the window size to half, and we drop the SS thresh also to half. But hey, as long as it's beyond the thresh, the window size grows linearly, then the design does not conflict, okay, with other parts of TCP's congestion window adjustment mechanism.
All right, so that was the entire TCP's congestion control mechanism. So the next few videos coming up is to introduce the finite state machine of TCP's congestion control. Okay, before we do that, let's attend to Mikhail's question. So Mikhail was asking, if congestion window, the CWND, oopsie, somehow I couldn't quite select. Okay, so let's just read Miguel's question. If the congestion window has already been reduced to half, and yet there's another 3 duplicate acts, does it get dropped by half again? Yeah, generally speaking, if in any case 3 duplicate acts is detected, congestion window size is reduced to half. So is the SS thresh. Okay. But later you will hear that there's an improvement of TCP's congestion control called fast recovery. It's not always that the congestion window sizes drop to half. The SS thresh is definitely dropped to half of the current window size, but the congestion window size might not be exactly half of the current congestion window size. Okay, so guys, pay attention. And I'm going to start by introducing, no problem, Miguel. I'll start by introducing the slow start part of the finite state machine. So you can probably imagine now, right? A TCP connection has 2 states. slow start state and the condition avoidance state. Exactly. So let's check out the slow start state first.
Now let's summarize TCP's condition control. And what I'm going to show you is actually a little bit more formal using a finite state machine. And you see how TCP sender here implements, okay, the mechanism of adjusting the window size. The full finite state machine has two states, okay. Each represents, different phases of TCP's condition control in a connection. The first is the initial phase, the slow start phase. Initialization transition here is actually initializing the condition window size to one segment, and then initializing the SS thresh to 64 kilobytes. I think this number could differ from operating system to operating system, and then initializing the duplicate add count. All right, so that was clear. Let's move to the normal transitions. There are four of them. Okay. If you look a bit closer, the top two here are actually the transitions handling the cases where the sender receives X. The bottom two are the cases where the sender detects losses. So this one here is actually detecting a loss due to receiving 3 duplicate X. This transition here is actually detecting a loss due to timeout. Now let's talk about each of these transitions a bit more. So number one here is if we receive a new ACK. Now, according to slow start mechanism, the condition window needs to be incremented by one segment, and that's it. So duplicate add count is reduced to 0 just so to clear all the duplicate add counts, because now we are receiving a new ACK, so we should definitely clear the dupe add count. And at this point, then we employ the rest of the sender's mechanism, the RDT part of it, so that we would slide the window over and then send new segments. And how much we send out there depends on the result of the condition control mechanism working. And next, transition number 2, this is when we receive a duplicate ACK. So what we do here, of course, increment the counter for duplicate ACK. And what do? The condition control power says no more, right? Unless the count here reaches 3. That triggers transition 3. Okay. Now in RDT of TCP, this event is going to also trigger fast retransmission. So in a way, when there's dupe add count equaling 3, then we do something for the condition control and then some more for the reliable data transfer. Now in the condition control, what we do is setting the SS thresh to half the window size, and window size to half of the current window size, which is now the value of SS thresh. And then reset the duplicate add count, right? And then we can begin doing the RDT, which is to fast retransmit packets. Now the number of packets we can send now then is determined by the condition window size we just set aside earlier. Transition 4, this is also packet loss, but this is packet loss detected by having a timeout. So in this case, the condition control says we need to set SS thresh to half of the window size, and the window size all the way down to 1 packet, and then reset the dupe ACK count. And then from here, the RDT mechanism, which is what to retransmit the missing segment. And because this time, in this case, condition window is set to 1 packet, therefore we only retransmit 1 segment. Okay, no matter how how many packets have been sent, how many yellow packets or yellow bytes are there in the sliding window. Right?
Yeah, so very straightforward. You see 2 transitions handling positive notifications, receiving X. 2 transitions handling the negative notifications, handling losses, and there are 2 different kinds of losses. Now, that is the initial state, okay, or slow start state. Let's check out the finite state machine, so the condition avoidance part of the finite state machine. And right after that, quiz 27 is coming up.
Done with the slow start state. Now, let's move to the condition avoidance state. So the first thing is, hey, when do we transition from SS to CA? Yep, when the condition window size is larger than the SS thresh. And that takes us to the condition avoidance state, where we see again, transition new ACK, transition duplicate ACK, transition dupe ACK count equal 3. And hey, where's the timeout state? Well, the timeout state is actually here, right? Because when we're in the congestion avoidance state, timeout is actually serious packet loss. We reset the congestion window down to one end. Yeah, start from the slow start. Increment the window size exponentially. Start from the slow start. So we need to do a state change in this finite state machine, going back from CA to SS. Okay. And otherwise, all these the same, just like timeout event. Similarly, for dupe egg count equaling 3, all the same, all the same. Okay. Actually, similarly for dupe egg, just incrementing the duplicate egg count. But the last one, the new egg, wow, we need to be careful here, all right? Because in SS versus CA, when we receive a new egg, meaning no loss, we actually increase the window size differently. So yes, this is why you see here. In SS, in slow start, we're incrementing the window size by 1 segment per egg. Here, we need to increase the window size by 1 segment per round trip time. So be very, very careful here. This is receiving an egg, not, hey, checking and we see that there's 1 round trip time elapsed. So we need to figure out exactly the amount to increment to the window size so that after 1 round trip time, the increment will be exactly 1. And how do we do that? Think this. If the window size is CWND and the packet size is MSS, how many packets will be out in one round trip time? Yeah, this many, isn't it? Okay. And after all these packets come back in, the increment of the congestion window should be 1. That is saying we cannot be incrementing the window size by MSS. We need to increase this much. Okay. After this amount of packets received, then we add to this value. So we need to divide this value by these. That would say this is the amount we need to increment per packet. Okay. So if we rewrite this formula here, it's what? MSS multiply, so MSS multiply reverse of CWND to MSS. So after reversing, MSS at the top and then CWND at the bottom. And that is TCP congestion control sender's finite state machine in a simplistic way. You see here, let me summarize again. Yeah, so these are the events receiving new egg. These are the events handling timeout. And these are the events handling receiving the duplicate eggs and it's reaching the count of 3.
All right, so now let's exercise the finite state machine, okay? Particularly on how the condition window size is increased, okay? So what I'm showing here in quiz 27, first is the finite state machine of TCP's condition control, all right? And you'll be asked about the condition window size, okay, of the sender when the threshold, slow start threshold A is 8, this value versus this value. So let me come back to the scenario. Okay, host N and host B, okay, 2 hosts, and A is sending data to B. The initial window size, hypothetically, set to 4 MSS, and the slow start threshold is 8. And so given it's 4 MSS and each data packet is exactly 1 MSS bytes long, then you will have the first packet being sent with sequence number 0. Let's assume that the sequence number starts from 0. The second packet then will have sequence number what? 1 MSS, isn't it? The second packet, 2 MSS. The third, 3 MSS. Okay, and in this scenario, we assume the third packet, which is the 2 MSS packet, is lost. Okay, so observe the first packet, sequence 0 MSS packet, arriving at the destination. It's going to generate what? An acknowledgement. And the acknowledgement will be what? Telling the source what is the next byte expected. So if it starts from 0 and packet size is 1 MSS, therefore the ACK sequence number should be 1 MSS. Similarly, the second data arriving at the destination, it would generate an egg that's 2 MSS. Now, the third packet is dropped, and the fourth one that carries sequence number 3 MSS will arrive, but there's a gap detected. What do we do? Yeah, data is not in order. So we send duplicate egg, right? So 2 MSS is the third egg. All right, now, makes sense. All right, now when the first egg, 1 MSS, arrive at the sender, hey, the condition window size should be changed, isn't it? Right? It's a positive notification. According to the condition control mechanism, B should be somewhat different from 4, isn't it? And it kind of depends on what the SS thresh value is. If A is 4 or below 4, then you will be using this state to derive the new condition window size. If this is higher than 4, then you'll be using this state, okay, to derive the new condition window size. I think you're getting the point of quiz 27. So that's exactly. So what is the value of B, C, and D upon receiving these 3 eggs? Q1 asks, consider the case A equals A MSS. Q2 asks, consider the case A equals 4 MSS. All right? Let's go to the score. Channel W10, quiz 27. Guys, Polly will be taking the fast solvers for bonus. So you have 4 minutes, and let's start counting time. Okay, Team 12 and Team 4, can you show the derivation? And Team 1, can you guys show the derivation? How did you get, for example, 4.25 and 4.5? I think Team 4, Zhenyu, I think the answer is correct. It's, wait, you just changed it. Yeah, it is correct, but not. I think it's correct, but you are probably rounding it up to a digit that is not exactly like mine. Okay. Yeah, Zhenyu, your original answer was correct, but just wondering how do you guys derive the values? Okay. All right, hey guys, time's is up. So yeah, the values are right, but I'm not sure how you guys come to the answer. I think you guys probably approximated it somehow. Yeah, I see more are typing, so maybe I wait a couple more minutes and see. Oh, Anthony is actually responding to the teammates. Okay, thank you. So I think Anthony is trying to show the derivation. Yes. So for B, 4 plus 1, because 1 MSS for each egg, incrementing 1 MSS to each egg. Therefore, C is also adding 1 MSS. And D equals 6 because there's no new egg, because the third egg is a duplicate egg, right? All you do is just to increment the duplicate egg counter. Very good, Anthony. Thank you. Okay, but I guess the tricky part is the Q2. All right, so numerically, you guys are correct. Okay, so but let's see. Okay. Oh, there. Great. Thank you, Team 5. Yeah, so Team 5 here shows the full derivation. Okay, so this is 4 plus 1 1/4, I see. Or is it just 1/4? Yeah, 1/4? Yeah, I think you meant 1/4. So I think it's just 1/4. Yeah. Yeah, I guess you guys did it by approximation. Oh, okay. Let me see. 厌期. But 1/0.25 is 4. Right? I think you meant 1/4 here, 厌期, right? Because you're right here. The condition window size when the next egg arrives in case A equal 4, which is the condition avoidance state. The window size is incremented by the current window size plus 1/, the current window size. And so if you do the calculation, it is 4.49, not quite yet 4.4. It's approximately 4.5, but not quite. All right, very good. I see. I think Sophia is trying to explain what Hongyu meant there. 1/4. Okay, good. So, hey, come over here. to the whiteboard. Okay, let me show the derivation. Okay, you'll see that it's quite straightforward. That when a equals 8, right? So we are obviously in the slow start state. So what we do is just to increment the window size by 1 for every new egg. So this was originally 4, therefore B is 4 plus 1, being 5. And C will be 5 plus 1, being 6. And duplicate egg doesn't increment the window size. Now, let's consider the A equal 4 MSS case. That is this case. Okay. So the way we increment the window size is defined here. So I'm writing it out a little bit bigger in font. CWND plus 1 MSS multiply 1 MSS divided by condition window. So in a way, in this quiz, I'm just assuming all the packets are constant size, okay? And I'm using packet count again. And so this is 1 packet, this is 1 packet, okay? So condition window size was 4 MSS. MSS multiplied by MSS divided by the window size, 4 MSS. So what do we have here? 4 MSS, a quarter MSS, together 2.25 MSS. And you guys get these perfectly. Now, guys, hey, do you send 4 packets here, or 5 packets here, or more packets here? Having 0.25 more in the window size. So if Poly has defined that the data is exactly always 1 MSS, then of course, we don't send more packet, okay, like this, okay, with only a quarter MSS. But in reality, okay, in real TCP, whether it sends 1 more or 2 more or more packets with small MSS, okay, given there's extra 1/4 packet size that you can send more, or 1/4 MSS you can send more. So it really depends on what the application layer calls are. In case the application layer asks you to send a 10 bytes, okay, which is much lower than a quarter MSS, then you will send that as a packet. And another, so you could send 1, 2, or more packets, okay, if you have a partial MSS. Okay, so this is just to clarify something that's in TCP, okay, which is not exactly like the RDT 3.0 or go back and selective repeat. We always count packets, okay, but incrementing the window size is always based on this formula, okay. So you ended up having this as the window size, which is okay, okay. And in this scenario, Poly kind of defined that each packet is exactly MSS, 1 MSS. All right. Now with that cleared, let's derive C. Okay, so C is receiving another packet. So current size plus MSS multiply MSS divided by the window size, right? So you write the same thing again. So all you need to do is just plug in the condition window size for the CWND variable. And so you kind of add these two up. So to be precise, it's 4.49. So every new acknowledgement, you increment it almost by a window size of a packet of MSS. So if the current window size is 4 MSS, so you can imagine that you increment 1 MSS about every 4 eggs. So the intuitions are correct. So let me go to the Discord again. So you guys' intuition is correct. It's almost 4.5. I have to say. But TCP, when it's following the algorithm and doing the calculation, Yeah, it is, calculating to fractions. So this allows more bytes to be sent, right? So Zach, very good intuition. All right. So during exam, I would suggest that you try to show the derivation so that we can see that you get the idea, okay, a little bit better. All right, great. Okay, so that was quiz 27. Okay, remember that Polly mentioned that there's a improvement, okay, of TCP's condition control, and that improvement is called the fast recovery. So this next topic, is to present the fast recovery. No worry. Okay, the video is short, even though the mechanism is a little bit complex. Okay, but the reason that I say no worry is because we have 3 quizzes coming next. Okay, to exercise fast recovery. So now you see, quiz 27 is to exercise how you do additive increase. It's not like for every ACK you receive, you increase the window size by 1. No. You increase a fraction of the window size. Great. So now let's play this fast recovery improvement video about 3 minutes, and then we'll take a break.
This finite state machine, now we walk through it. It's kind of symmetric and clean, relatively easy to track. This is also the mechanism implemented in the TCP Tahoe, the version 1. In TCP Reno, it's actually being extended. So the hack here is called the fast recovery. Okay. Now, this version looks substantially complicated, but let me tell you this, hopefully makes it a bit simpler for you. The only transitions that are actually touched from the previous finite state machine are just these. Okay, the case where the dupe at count reaches 3. So previously what we do is this. We set the SS thresh to have the window size and the window size to SS thresh. But now, okay, in Reno, we actually add 3 more segments to the window size. So we're actually a little bit more generous about setting the window size. And the logic behind this is, hey, if we receive 3 duplicate ACKs, that means the channel between the sender and receiver, there's enough capacity to allow 3 data segments to go. Although out of order, still triggering duplicate ACKs to come back, right? So 3 spaces, therefore generating 3 duplicate ACKs. So there's enough capacity, right? So we don't have to go all the way down, okay, or half down. So as long as, hey, we're seeing, duplicate ACKs, that means the capacity is still there. Maybe this is just a very, short-term condition, short-term precondition, okay, happening. So maybe we just keep, pushing a little bit more, and when this short-term outage or short-term condition goes out, then we can come back to normal. Okay, so this is the logic behind the fast recovery mechanism here. So after adding 3 more segments to the window size, we enter the fast recovery state. And staying in the fast recovery state, we apply the same logic. As long as we receive a duplicate ACK, we continue to increment the window size. Because being able to receive a duplicate ACK is because we allow 1 data to go out, right? Yeah. So this is going to be repeated until what? Until we finally get a new ACK back, or all these extra packets we send out by being more generous about the window size somehow get dropped in the middle, meaning the congestion is not short term. It's a bit more pathological, persistent. So we will run into timeout here. In this case, drop the window size to 1, feel free. But if it's in this case, it's okay. Then we can just reset the window size to normal, which is half of the window size, and then go back to the congestion avoidance states, and then begin linear increase again.
There, fast recovery. So a new state is introduced to the total finite state machine. And that state is kind of a temporary transitional state there, okay, when the 3 duplicate ACKs are received. And to exit this transition state, there are 2 conditions. One is, very unfortunate, timeout still happened. Then you go back to the slow start state. Now, in case a new ACK is received, then great, let's exit and go back to the congestion avoidance state. Okay, but why? Why having such a transitional state, right? 3 duplicate acts, then don't we just stay in the condition avoidance? Why do we need a fast recovery state? Okay, so I hope that with quiz 28 to 30, that brings something out and tell you why fast recovery is a good idea. And in order to do that, let's take a break. 10 minutes, it's 11:10 now, and we'll resume at 11:20 and we'll go through 3 quizzes and see if you can observe the benefits of doing fast recovery. Okay, break. So it's now 11:20. Let's go on with the next quiz, okay, 28. So this quiz is about fast recovery very much. Okay, so this is the first in the series. So what you can see is the same scenario, what we just did to figure out how to do EI and AI. So up to this point, all the same. Okay. Now you see also that upon receiving Act 1, okay, previously we increment this to 4.25, right? So it's incremented by one of the condition window, okay? And another new Act, so we incremented it to 2.4 something, right? 4A something. And guys, in this scenario, you see when the window size is 4.25 and we are just sending one more packet out. Okay, so this ACK, 1 MSS, generates only one packet out. This means in this scenario, I'm assuming if the window size is partial, this TCP connection does not send additional packet. Okay, so this 1 MSS arrives, although the congestion window size is increased, and the window size is slided over, right? Because packet 0 is acknowledged. So we slide over. So this packet is just sent because there's one packet available, 1 MSS available. In fact, 1.25 MSS available. So in this scenario, when the congestion window size is not a full MSS, this connection does not send any packet. So in a way, this connection will buffer all the data until it's exactly MSS large before sending it out. Okay, so that's why you see that as a result, only one packet out. When receiving Act 2, oopsie. When receiving Act 2, window size 4.4A something, still not one full MSS, but we slide the window over so we can send one more packet out. Okay. Guys, what is the sequence number of this packet? And what is the sequence number of this packet? Sorry. What is the sequence number of this packet? And what is the sequence number of this packet? So this is a new ACK. So this is generating a new data. So this was 0, 1, 2, 3. Therefore, this is segment 4 MSS, and this is segment 5 MSS. When 4 arrive at host B, it will generate an ACK. What is the sequence number here? Well, it's still out of order, right? So 2 MSS here. Similarly, segment 5 MSS will still generate an ACK 2 MSS. And guys, this is the first ACK that says 2 MSS. This is the second ACK that says 2 MSS. This is what? The third and the fourth. So in a way, this guy here is the third duplicate ACK. So this is the point. We receive 3 duplicate ACKs. Now, can you tell me what would the threshold be and what would the window size be without fast recovery versus with fast recovery? And this is what quiz 28 is about. Okay, now let's go to channel 10, quiz 28. Guys, I'm also taking fast solvers for this quiz for bonus. And let's give it 4 minutes time, okay, just like the previous quiz. If possible, show the derivation. Okay. Yeah, you know what? So as I'm seeing the derivation, I see that you guys get it right. Yeah, so it's essentially E should be half of D, right? And F should be, yeah, F should be E when there's no fast recovery. Very good. And F should be E plus 3 with fast recovery. Fast recovery. Very good. And E is half of D. Very good. Perfect. Yeah, so guys, in case you worry that whether you get the numerical values right or not, the best way is just to show the derivation. Okay, that way you will be always correct. Let's see. Team 3. Half the window size, which is currently 4.48 something. Very good. And for Q2 with fast recovery, and this condition window size is, yeah, plus 3 MSS. Very good. Yeah, guys, you see, exactly, right? Because the way TCP increases the condition window size does not always give you a integer value. So it's a little bit hard to really grade a fraction. Okay, so show me the derivation. Perfect. Okay, E is half the okay. Yeah, that would solve your problem, right? Which fraction is exactly right? Yeah, half of the window size, and then for the fast recovery case. So guys, I think you guys are getting it. So if we come back here to the whiteboard. So what is the difference here? Essentially, the value of F. Without fast recovery, you are stuck with 2 point something. But with fast recovery, you get 5 point something, right? So you can have potential of sending more data out. So guys, this is segment 0, 1, 2, 3, 4, and 5. And we have already added these two. So there are 4 packets still in flight. And 5 is bigger than that. So that means potentially the sender can send 1 more packet, right? Okay. That is what fast recovery is doing. Okay. In fact, the condition window size is given a higher amount of buffer to allow the sender to keep pushing. Okay. In fact, if there are more duplicate eggs coming in, the condition window size will be incremented further, as if these arrival of duplicate eggs are also a good thing, like a positive notification. Yeah. So it's a negative condition, but slightly positive news. So fast recovery is to allow the situation where this drop here is just a random drop instead of a drop due to congestion. Sometimes on the internet you could have random drops. This is especially the case when between host and B there is a particular segment being wireless. In a wireless link, there's a higher chance of having random packet drops instead of drops due to buffer overflow. Okay, so that's the point of fast recovery. Now, guys, careful. Even though you see that the F here is 5 point something in fast recovery. Okay, let me ask the next quiz. Do we transmit a packet with F being 5 point something? That is quiz number 29. So continuing from quiz 28. So let me ask, any packet sent at third duplicate egg here? This is the third duplicate egg, we know. And we know when this arrives, the sender changes E and F. Does sender send a packet out? In both cases, without fast recovery and with fast recovery. Okay, let's go to the Discord. Channel W10, quiz 29. Guys, look up your finite state machine, all right? Do we transmit a packet out? You guys have 3 minutes this time. Again, fast solver gets bonus. I know you see fast recovery's finite state machine. How about the finite state machine without fast recovery? Okay, so you might want to go to the course page and go get the slides or roll back the video a little bit. Right, transport layer, I think. Yeah, where's the finite state machine? Without fast recovery. Let me see. Oh, there. Yeah, I think this is the finite state machine without fast recovery. Okay, upon 3 duplicate acts, does it send a packet? Okay. Yeah, so many of you probably realize, hey, this is a trivial question. It is. Okay, it sends a packet. Very good. Okay, Yongxiang, you're getting it. Yeah, just more specific is always better. Yeah, retransmit the missing segment. Okay, keep that in mind, Yongxiang. Very good. Both. Yeah, upon 3 duplicate acts, retransmit the missing packet. And just the missing packet. Okay, so guys, let me come back here. So even though F is 5 point something, this is still the retransmission of the missing packet. Okay, keep this in mind. And let's move to the next quiz. So this is the last one in the series. You see, yeah, we do send a packet upon receiving the third duplicate egg. Can you tell me what is the sequence number of this packet? Again, without fast recovery and with fast recovery. This time, you have only 1 minute. Let's go to the Discord. Channel 10, quiz 30. 1 minute. Similarly, fast solver gets a bonus. I think I get you guys. Very good effort, guys. I know what you guys are saying. Hey, it's this packet. So let's come back to the whiteboard. Yeah, this is the missing packet, right? It is obviously the third packet, but what is the sequence number of the third packet, guys? There you go. There you go. There you go. The missing packet. Very good. Very good. Yeah, sorry. You see that it can be a little bit tricky, isn't it? It can be a little bit tricky. The rules are simple, but when you are really using it, not as a computer running a strict program, it can get a little bit. It's not exactly confusing. It's just a little bit tricky. You know, it's the third packet, right? Packet 3, but the sequence number of packet 3 is 2 MSS. Okay, so with this series of quizzes, now you see. Yeah, the reason that we have the fast recovery is not only retransmit this packet, but with fast recovery, so F here is 5 point something, we could keep transmitting, okay, for cases where the drop here is just random, not because of a heavy traffic low. Great. With that done, let's move on. Yeah, guys, TCP's condition control, very often when Polly is talking about it, sounds so easy, but if you try to follow the finite state machine and work it out, you will see that it's not exactly that trivial. Okay, not exactly that trivial. So before taking the exam, you want to try the old exam questions and exercise, okay, these finite state machines more. Okay. Now, the next two topics, modeling and fairness. So these are actually issues that people, or research problems that people are working on to try to optimize TCP. And modeling is to optimize the throughput, the performance. Okay, so this next video, I think about 5 minutes, talks about people trying to model the throughput of a TCP connection.
Let's cover two more topics related to TCP, and these are about what the research community is doing trying to improve TCP for the future need. First is about how one improves TCP such that it can support long, fat pipe. Okay, what I meant by long pipe is a TCP connection that has long round trip time. And a fat pipe is that it has high throughput. Okay? And this is what we know. Okay? Sending rate or the throughput should equal the window size divided by round trip time. So this is 0.1 second. And the rate should be 10 gigabits per second. So you see the congestion window is essentially the two terms multiply, and that is 1 gigabits and approximately 110 megabytes. So at the sender side, receiver side, 100 megabytes is required to buffer the packets that are in flight. And this is just to maintain one connection, right? If you have 10 connections, that's already 1 gigabyte of memory. If you have 100 connections, that's gonna probably take all your memory away. This is just one issue. Another issue is this. TCP is actually go back and like. What if you run into a packet loss that is triggered by having 3 duplicate acts? What we do there is we set the window size to half of the window size before a loss event is detected. And you know what? The window size, the number of packets there could be, can be as high as this, because if we divide this by 1500 byte, you get these many packets in flight. So in that case, we'll have to retransmit all the unacted packets, okay, and half of the window size here, okay? So that's, wow, 41 and 666 something packets that we need to send. The bandwidth consumption there, right? The amount of bandwidth we might be wasting there is very significant. So TCP, the current design, isn't really ideal to support long fat pipes. And this is actually assuming that there's no packet loss at all, no bit error at all. What if we have error? One will have to derive the TCP throughput model considering loss before one can see how big a problem it is to try to support long fat pipes. So let's try to do some derivation here and see if we can come up with the average TCP throughput, okay, provided the window size, round trip time. The assumption is that let's ignore the slow start, okay? Consider just the congestion avoidance operation and assume that there's always data coming in. And the scenario is very simplistic, which is illustrated here. Over time, the changes of the window size is exactly from half of W increase all the way to W, and W is where the loss will always occur, and therefore we drop the window size back down to half W because this is in condition avoidance. When there's a loss, drop to half W. When there's a loss at W, drop to half W. Okay. And so it's not hard for you to see what is the average window size? Yeah, the midpoint here, right? So 3/4 of W. And therefore the throughput is what? The average window size divided by the round trip time, which is this term here. Now, if we plug in, yeah, this is the goal throughput, and this is the round trip delay. Now, what is the window size now? Well, it will be this term multiplying each other and multiplying the reverse of 3/4. Therefore, it's 4/3 now. So this is actually even bigger than the CWND we're calculating there. So with loss, yeah, the amount of memory required to store data higher, the amount of unnecessary retransmission also higher. We can go on and on, right? Try to derive a more general model. So let me not go over the exact derivation, just tell you, if the loss probability is L, okay, one can actually come up with the TCP throughput being represented this way. Round trip time here, okay, square root of L here, and the maximum segment size here. Okay. Now, if, take the same example here, take the same setting there. Packet size being 1500 bytes, round trip time being 100 milliseconds, and the goal throughput 10 gigabits per second. In order to achieve so, the loss rate needs to be as slow as this. 2 multiply 10 to the power of -10. Okay? Now this is a loss rate that's also impossible pretty much on the internet today. All right? So definitely we need new versions of TCP to support very high fat pipes going a long way.
Yeah, so you see, TCP is not that good to support data center, data transfer, backup data transfer between the data centers. Okay, those are the long and big pipes. So with that low loss rate, that is pretty much impossible. Okay, now another topic is about improving fairness, okay, of people using the internet. I recall yesterday, right, several of you asked, what if we have other traffic that is blasting data into the internet, okay, unlike TCP trying to control? That doesn't sound well exactly, because that is not fair. So this video talks about fairness, and TCP comparing to transmitting data not using TCP, obviously, okay, is weak. Using other means such as UDP, you can always push as much data as possible, okay, and causing some congestions. But something that's really nice about TCP is this. A TCP connection versus another TCP connection, no matter what time they have started, what is the state of the window size of these TCP connections, they will all eventually converge to about similar condition window size. Therefore, these TCP connections, regardless of the starting time, will eventually be self-fair to each other. Okay, that is what this video is about.
Another major issue is this, fairness. Okay, let's talk about fairness at this level first, the TCP fairness. Okay, so what we're talking about here, the goal is to make sure that the K TCP sessions will share the same amount of bandwidth if it go across the same link of bandwidth R. So the eventual share of the sending rate or the throughput should be R divided by K. Okay, so in this scenario, what you're seeing is the router in the middle, the capacity is R, and we have two connections. So connection 1 here should have half of R, and connection 2 here should have the equal amount. So we have two competing TCP sessions, and they're competing for a link with capacity R. So what I'm showing here are the relationship of connection 1 and connection 2's throughput. So one extreme is connection 1 gets the whole R, while connection 2 gets nothing. And this is the other extreme. Connection 2 gets R, while connection 1 gets nothing. The fair point is right here in the middle. Okay, each of them gets half of R. So you see here, the dotted black line is to draw the equal bandwidth share, meaning if the bandwidth of connection 1 and 2 falls on this black line, yeah, they'll be fair to each other. Now, the blue line here, okay, is actually illustrating, this is actually the boundary, the capacity of the link. Okay? If the sum of connection 1 and 2 throughput goes beyond the blue line, that means congestion is beginning to occur, packets will begin to drop. Now let's say we start from here. Connection 1 having this much throughput, while connection 2 have very small throughput. As time goes by, okay, we're in congestion avoidance state, so we will continue to do additive increase. Therefore, connection 1's throughput will continue to increase, just like connection 2's throughput will continue to increase. And the characteristic, the value of connection 1 and 2's throughput will fall along this line here with the slope of 1. Now, as it goes beyond the blue line here, this is actually beyond the network capacity, we'll begin to see packet drop. And what we'll see next is what? The two of them reducing the throughput to half of the value here. Okay, so this is connection 2's. Connection 2's throughput drop to half of it. Okay, right down here. Connection 1's throughput drop to half of it, right down here. Okay. So having a loss, decrease the window size by a factor of 2, and that takes us from here down to here. So this is the current throughput of connection 1 and connection 2. Let's move on, right? It will continue to go additive increase as we are in the congestion avoidance state. Crossing the boundary of blue line, drop packet again, and decrease the window size again. Okay, again by factor of 2. So we go down here. So you see, additive increase, multiplicative decrease, additive increase. You see, the throughput of connection 1 and 2 are actually what? Approaching the equal bandwidth share. So TCP between the connections, the mechanism warrants that they will be fair to each other. So we see between TCP connections they'll be fair to each other. But what about TCP to UDP? Multimedia applications actually prefer not to use TCP because TCP has this window size mechanism when there's congestion drop it, right? So the rate, sending rate is actually throttled by the congestion control mechanism. So some of the multimedia applications would prefer UDP, and they would send audio video data at high rate, constant rate, without really adapting to congestion. So would that be fair? Of course not. And not to mention this, what if you have applications who open up multiple parallel TCP connections, okay, versus other applications who opens one TCP connection at a time to send data? Now consider this case. A link of rate R with 9 existing connections already, right? Then each have R over 9 share of the bandwidth. When there's a new app coming in asking for 1 TCP, that app then will share with 9 existing connections and each get 1/10 of the R. But if the new app comes in and then asks for 9 parallel TCP connections, so that will be what? R dividing by 9 plus 9. And each connection is this much because the new app gets 9 of these, so let's multiply this by 9. New app gets half of R. So a new app designing this way versus a new app designing this way, okay, competing with other existing connections, it's actually hard to make it fair. And you know what? Web browsers these days do this. Okay? They might start parallel connections to fetch one page. Previously, Internet Explorer were very aggressive. Okay? For example, starting 8 parallel connections, 4 parallel connections to try to fetch web objects in a page. But nowadays, the HTTP consortium actually regulates so that they do not overdo this.
Yeah, so you see, TCP connections will be fair to each other. TCP and UDP, TCP is no competition. And then there's another level of fairness which is happening at the application layer, which means if a web browser will start multiple TCPs at the same time, that web browser starting more TCP connection in parallel at the same time will actually get an advantage over those who don't open up that many parallel TCP connections, you see? So in short, it's a little bit hard to make sure the world will be fair. Okay? But TCP at least tries to make sure that all the TCP connections will be fair. And that is actually done also magically by the AIMD mechanism. Remember? And I actually showed the animation, and that is also in quiz 31. Okay, so you see here, the initial state, the two connections might be having a throughput that's not exactly fair. Okay, so connection 1 gets more, connection 2 gets less. But with the AIMD mechanism, you see that it would gradually approach the equal bandwidth share. Okay, that is really cool, isn't it? And that is something that we talked about yesterday, right? In the quiz 26, we were very aggressive, binary search. Okay, if we keep doing that, that will be very aggressive. Sometimes you might end up having oscillations. But AIMD is something that is really nice and always draws to stable states in a control system. All right, so quiz 31 asks, would these two connections, connection 1 and 2, converge to equal bandwidth share if the CWND adapts using these other mechanisms instead? What if the adaptation is AIAD, additive increase, additive decrease? And what if it's MIMD, right? So both connections, okay, will need to double. Okay, so this double, so you go like, ooh, and MD, multiplicative decrease. What if it's MIAD? On the increasing side, multiplicative, but decreasing side, additive. Okay, so this is quiz 31. Let's go to the score space. Guys, you have 5 minutes. Okay, Polly. Oh, okay. Team 4, too fast. Okay. Yeah, Polly will take. Yeah, fast solvers. As bonus. For bonus, yeah. Okay, so let me check. Yeah, so I guess that the problem is actually not that difficult. So if we go back to the whiteboard mode, so what does AIAD do? So you go AI and AAD, AI and AAD. So you get stuck here, right? So it never really approaches the equal share. So obviously, AIAD, no. MIMD, as Polly tries to illustrate, right? Starting point is here. So we double this, we also double this. You go like this, up, but you also go like this, down. So MIMD also doesn't converge to equal bandwidth share. Now, MIAD then will be going this trend up, but AD, don't this way down. And when you increment, you go this again. So it kind of diverge somewhere, okay, eventually way up. And the equal bandwidth share is very likely after a while way below, okay, that regime that you are oscillating. So AIMD might, MIAD might be a little bit tricky, but eventually, okay, asymptotically, it will not converge to the equal bandwidth share. Okay. All right, so that's quiz 31. And you know what? Yeah, we have just one last video to play about congestion control, in fact, for chapter 3. That is called the ECN. Okay. If you recall at the very beginning when Polly was talking about the two approaches of doing congestion control, one is end-to-end approach, the other is what? Network assisted approach. TCP, yeah, the commonly used TCP takes the end-to-end approach. There's an option in TCP that is rarely in use now. That is the ECN option that takes the network assisted approach. This short video, I think 3.5 minutes, talks about how ECN works.
That was TCP, taking the end-to-end approach. Let me introduce another mechanism that's called the ECN. It's also defined for TCP/IP for the internet, but it's not really implemented or activated. And it's taking the opposite approach, the network-assisted approach. The ECN mechanism works this way. First of all, in the IP packet header, okay, or network layer header, there's this special field called TOS that stands for type of service. So in that field, 2 of the bits are assigned for the purpose. They are also called the ECN bits. Okay, so I'm using a green packet here to indicate that that packet header, especially the network layer header, is carrying the ECN bits. They were initialized to 0, that means no congestion, but as the packet travels through the network, running into a busy router like this, the bits will be turned down. And the packet will eventually come, okay, and arrive at the receiver of the data. And the network layer here at the receiver is going to see, oh, these 2 bits are turned on, therefore notifying the transport layer. And at that point, okay, the transport layer of the receiver is going to do this. Receiver is going to set the ECE bit on the packet, going back to the data source, like this. Okay, so it's going to be in the ACK packet, and the ECE bit being turned on. So this is also called the E flag, okay, in the TCP packet field. Sender there, upon receiving this ECE bit packet, will then send a packet that is then the data packet going back to the receiver. And that packet is a little bit special because there's also a special bit being turned on, the CWR bit. So this is congestion window reduced bit. This is so that the destination here, the receiver of the data here knows that, okay, so my notification here, you indeed received it and reduced the sending rate. Okay, so therefore the receiver of the data does not need to send ECE bit again. Okay, otherwise, the source is going to reduce sending rate again and again. Right? And the E bit and the C bit, the E flag and the C flag are in fact, again, in the TCP packet header. Okay, so along with all these other flags for TCP. And that finally takes us to the summary of the chapter 3. We went through the basic functionalities of transport layer protocols: multiplexing, demultiplexing, reliable data transfer, flow control, and just now, congestion control. And we talk about how UDP and TCP implement these services. Particularly, we spend quite a lot of time here, as well as here. We are now finally ready to leave the network edge. So departing from the transport layer and down to the network layer and into the network core. But the network layer is going to be split into two chapters. Chapter 4 is going to be about the data plane, how we forward packets real fast. And chapter 5 is going to be the data plane. So how do we control these paths we select such that the packet will travel and eventually reaching the destination, reaching the receiver.
All right, so that's chapter 3. Coming next is chapter 4 and 5, the network layer. So network layer is significantly more complicated, and we'll split the mechanisms implemented in network layer in 2 chapters. Okay. Now, given the time we have remaining, we will not get into chapter 4. And the amount of videos I have forecasted for you guys to watch next week is perfect now. Okay. But we do have a little bit time left today, so maybe we should go through the questions from the students. So Sylvain here says, how are the new versions of TCP developed? Okay. Very good question. Yeah. So these developments must have been paid by someone. And where did the money come from? Okay. Somehow TCP is free to use. Well, hey, this is a mini question, Sylvain. So first of all, how is TCP developed? Okay. So when we say developing, we usually mean that thinking of a mechanism, okay, and then go on and implement the mechanism. Okay. So go on and implement the mechanism is partly by the big companies, partly by open source effort, and partly by the research people. So big companies such as Microsoft, such as Apple, because Apple has its own operating system. So every operating system needs to be able to connect on the internet these days. So therefore they need to implement TCP, right? Each machine running whatever the operating system is a host. Okay, this host, if it wants to communicate with other hosts on the internet, it needs to implement TCP UDP. And so each of these companies shipping operating systems with their hardware will definitely invest money into implementing the TCP so that it will interoperate not only with the company's machine, with their own implementation of TCP, but also other machines, Windows, Linux, other operating systems TCP. Okay, so big companies usually invest money into implementing these protocols. Linux, for example, is of open source effort. And BSD, for example, from Berkeley, okay, is research effort to begin with, and then later on open source effort. Okay, so implementing of TCP is a combination of all these institutes. Okay, and the design of TCP, however, is a little bit complicated. Okay, because every company might be in favor of designing TCP one way versus another. For example, Google would really like to drive TCP towards the direction of being capable of sending a high amount of data, big long pipe TCP. Okay, because Google has quite a few data centers around the world, and if they want to sync data, they do need the big long TCP pipes. Okay, so there's an organization for all these major players on the internet to try to sit down and discuss or debate, okay, what new features we want to add to TCP or other protocols. That organization is called IETF. Hey, August, exactly, yeah. So Quick is also a very popular protocol these days. And it's standardized by IETF. So IETF stands for Internet Engineering Task Force. So that is the organization. Hey, by the way, there's an event, IETF event going on in Finland right now, I think, or maybe next week. Yeah, so IETF people gather like every half a year at least. Okay, and there might be some local events as well. I think there's also a branch here in Taiwan and Japan, and yeah. And these guys very often need to sit down and talk. Prague, yeah, exactly, sorry. Yeah, it should be Prague. Yeah, I recall it somewhere in that area. In Czech, Prague. Yeah, so IETF events, and these big companies will definitely ship people there to talk about what should be in the next version of the standard. All right. So that is the design part of the development, and it's done by all these major players. Yeah, so these guys in IETF do have a lot to talk, and a lot of times each company will propose something and try to appeal the other companies to support the change. Okay, and they will also vote. When a particular change is favored by a majority, then they vote and include that in a RFC. So initially it will be a IETF draft, but eventually when it's approved, then it will be called a RFC, request for comments. Okay, I don't know why it's called request of comments, but yeah, so request of comments is actually the standard, okay, of what IETF come up with. All right, thank you, August. And you know what? That's all the time we have, and I'll see you 2 weeks from now. Okay, no lectures next week, but definitely go over the videos, and I'll make sure that I post I don't know, sometimes IETF also do live stream, so you guys can try to follow and see what they're talking about. Okay. There are many conversations about security, many conversations about higher level protocols, video, application, transaction. Less conversation about the lower levels. Now we have software defined networking, which is coming ahead in chapter 4 and 5, guys. So I see you 2 weeks later. Bye. Okay, bye. All right. Interesting. Yeah. So there might be some streams, but it's not responding. Oh, there. Okay. Closing.